What's going on, everybody? It's Mr. Gustin. I am back in the physics classroom. Today we're doing the Atwood Lab, elevator lab, and I've got it set up over here on the wall. So I've got these two massless pulleys attached up here. There's a string, a fairly massless string over the top of them, and I have two hanging masses. If you can see this far, object 1 I'm saying is 100 kilograms, and 100 grams, and object 2 is 200 grams. This is the mass of these two hanging masses. Now, obviously, hopefully you're sitting at home right now going, Mr. Gustin, those things are not accelerating. There's no way there's unbalanced masses there. And you're right. Right now, I've got two 200-gram masses on there just to hold it steady so we can kind of get a sense of our picture here, okay? Because as soon as I put unbalanced mass on the side of this thing, it's going to accelerate up and over. And we don't want that to happen yet because I'll be resetting this thing up nonstop. So I want to give you some data, talk through some basic stuff here originally so we can kind of prime our brains for this lab. Now, there are two parts to this lab. The first part is theoretically determining the acceleration of this object or this system, and the second part is experimentally determining the acceleration of this system. So let's first do a little theoretical stuff, okay? So when I think about these objects, I'm actually going to draw them, I guess, near here. So here's object 1, and here's object 2, which is a little bit bigger. When I think about these objects, there are forces acting on them. One force that acts on both is gravity. I see the gravity from object 1 over here, and then over here, there's the gravity from object 2. Now, gravity on object 2 should be much larger because it has a larger mass. The other force, I got to think about the force that is going to pull up the lighter mass. The force that's going to pull on my lighter mass and pull it up is a tension force. And if I think about which way this object should go, the tension force should be larger than Fg1. Because when this is a lighter mass, this system is going to go up and over this way. So tension is the force that is going to accelerate this object upward. Now, over here, the force tension force on object 2 should be less than object 2's weight force because the downward force is quote-unquote winning. It is the one that causes acceleration. So over here, if I'm ranking these forces, Fg2 is greater than tension on 2. The last thing we have to consider, and the reason this Atwood problem falls where it does in our unit, is that both tension forces are equal. They are considered a third law pair, right? Basically, this tension force pulls up on this string, this tension force pulls up on this string. There are equal forces here in the string. And so tension 1 and tension 2 are the same force. They are an internal force, which means they do not affect my system, but they do affect the individual objects. So based on what F net expression, what I'm examining in terms of my mathematical and my theoretical calculations, tension force may or may not be useful to us, okay? So what I want to think about first is I want to find the acceleration of my whole system. And so I can have two different F nets, right? I can have F net on object 1, and that would be equal to the mass of 1 acceleration, and we know that's going to be my tension force minus Fg1. And I can do the same thing over here, right? I can go ahead and say F net on 2 is the mass on 2 times its acceleration, Fg2 minus Ft2. Now, why do I flip the direction? Why do I flip over here, gravity is negative, and over here, gravity is positive? If I think about this system, when I do release it, when I release this system, if this is my lighter mass, what I'm going to see is that my left mass, or my object 1, is going to accelerate upward, and mass number 2 is going to accelerate downward. That means that anything, the direction of acceleration is up over here, and it's down over here. That means on object 1, I want any forces that are causing acceleration to be positive. Any forces that are hindering acceleration, I want those to be negative. Same thing over here. When this thing falls, I want all things that are causing it to fall to be positive, and all things that are resisting that fall to be negative. This will help translate between the two objects and help my analysis with numbers better. But now, if I'm trying to find the acceleration of the system, neither of these equations, neither F net 1 or F net 2 truly help me because I don't know what the tension force is. And if I don't know what the tension force is, well, then I really can't figure this problem out. So instead, what I should do or can do or might try doing is finding an equation in which tension is not wrapped up in the equation, where tension is not causing motion. And so for us, that would be the system. Let's look at the entire system. What is the system? The system is the two-mass system connected by the strings. So I'm going to come over here and write an F net for the system. What are the forces that act on the system in total? Well, those forces are, I guess this is mass of system times the acceleration. That's going to be equal to the force that causes the acceleration. That's Fg2. Fg2 is the one that causes the entire system to accelerate in this way. Now, Fg1 is like hindering it. It's working against Fg2 because they're attached over this pulley. So I'm going to say Fg2 is my accelerating force. It is the force responsible for the motion. And then Fg1 is responsible for this system not being in free fall. It is holding back against Fg2, but it's losing. So this is my system. Notice, this equation does not have tension. That's a good thing. So I can now solve for acceleration. Do I know Fg2? I know mass. I know the mass on 1. The mass of my system is just total mass. So we can actually go ahead and solve this. All right? So my mass of the system, that's 0.150. No, hang on. What are my objects? 0.3. I'm sorry. It's 0.30 kilograms. It's 100 grams plus 200 grams is 300 grams divided by 1,000. I get 0.3. Now I'm looking for the acceleration of my system. That's equal to Fg2, which is also mg. So mg would be 2.200 times 9.8 minus my 0.100 times 9.8. Okay, the acceleration is going to be equal to that product divided by the total mass, which is 0.3. Now, if you want to solve this, go ahead, you solve it. You pause it here. You can solve this outright. You can actually also then go ahead and solve for tension. If you want to do those things, go ahead and do those things right now. I'm about to put the answer on the board. So if you don't know the answer yet, you practice your algebra here. I end up with the acceleration is 3.27 meters per second squared. This is considered my theoretical. My theoretical acceleration. Why is it theoretical? Because I am not taking into account any of the errors or frictions or anything going on here. I am saying, in theory, according to Newton's laws and FBDs and the second law, this should be my acceleration. It should be. That's theoretical. Experimental is going to be once I start my experiment and take my data, that's my experimental value. Okay? So as we move on to the experimental, let's look more closely. If I'm going to experimentally determine this this acceleration, what I want to do is take some data. And that data is going to include distance and time. So I'm going to go ahead and kind of share this with you. I am not going to do your theoretical for you. I will show you the data. I'll write the data down, but I need you to go ahead and calculate what your your experimental is. So, a couple things here. I will go ahead and get height. This object is going to fall a height of 180. Let's see here. You know what? I'm going to change this out. I am going to go ahead and put my 100-gram mass on here now. That way I can measure the bottom of the 100-gram mass. The 100-gram mass is going to fall 189. So I'm going to mark it right here. This is 189 centimeters from here to the ground. That's how far this thing will fall. All right? Now your job, and it looks funny because of the angle of the camera. I promise I've marked it kind of right there. You're going to time this thing until it falls that distance. So I'm not taking time. You're at home. You're watching this. You take time for this lab. So let's go ahead and try that. This thing is going to cause a headache when it hits the ground, because it's going to launch this thing up into the air. I'll try and catch it if I can, but I'm going to drop it in 3, 2, 1, go. Missed it, but I caught it. I caught it. That's pretty cool. That's kind of nice. All right. The string came off. You should be able to time it. And if you want to, we can do the exact same trial. You can just go back, forth, back, forth, back, forth in this video and take 3 different times because it shouldn't be a different time. The only reason we would do multiple trials is because of your reaction time. So you can watch this video back 2 or 3 times, average those times out. Again, it fell 189 centimeters, 1.89 meters, and you find time. Use your kinematics, find your experimental acceleration. Hopefully it's pretty close to our theoretical if things all worked out according to plan. Okay? You now have the data for the elevator Atwood Lab. We've walked through an elevator Atwood type problem to find acceleration. You could also find tension force if you'd like to. That's also part of the analysis. All right? Good luck with your lab. Until next time, see ya!